All right, so in this video, we're going to find the Taylor series centered at 0 or Maclaurin series for the function sine of x. So remember, a Maclaurin series is nothing but a Taylor series in which we center at x equals 0. So all of those a's we're going to just evaluate at 0. So in our general kind of Powe series, Taylor series recipe for sine of x, again, this is the function that we're choosing. So all those f's and f primes, f triple primes, double primes, etc., are all of the function sine of x here. We're evaluating all of those a's are just 0 for us. So everywhere we have an a in this general Taylor series recipe, that is really just turning into a 0. Because again, we're looking at the Maclaurin series formation of sine. All right, so if we just do that, let's actually take a look at what we're looking at here. So sine of x is just going to be equal to all of those terms that are highlighted in blue, are those coefficients coming from the Taylor series itself, and then we have x's raised to the according powers of x. So let's actually see where the series for sine comes from. And just as a spoiler, remember what we are expecting to see. So this is a spoiler from before, is that we saw that the series for sine looks like the following. It's the infinite series n equals 0 to infinity of -1 raised to the power of n times x to the 2n plus 1, all divided by 2n plus 1 factorial, where the first couple terms of the series are x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so forth. So let's actually see where this series comes from. And we're going to do this in a slightly different way than what we did for the exponential. I'm going to first make a table of values just to help us keep organized here. So this table of values in which I'm going to do will just be n, the function's nth derivative. So this will just be the nth derivative of sine evaluated at x. Then in the next column will be that nth derivative evaluated at 0. And then finally, we'll put that coefficient together. So the nth coefficient, again, is equal to the nth derivative evaluated at 0, information coming from the previous column, all divided by n factorial. Let me actually just space some of these things out a bit. So let's start computing some derivatives of sine. All right, so we'll look at these corresponding index values. So when n equals 0, again, the function's 0th derivative is just the function itself. So in this case, that really just is sine of x. So if we again go over here, evaluate the function itself or sine at 0, well, that just gives us a big old 0. So it turns out for sine, the C0 term is equal to 0. All right, let's take a look. When n equals 1, we get the first derivative of sine, which is a positive cosine of x. And then if we evaluate that cosine of x at 0, well, that is equal to 1. So the C first coefficient of our sine series is equal to 1, which is coming from that functions of derivative evaluated at 0, all divided by n factorial, which in this case is 1 factorial. All right, let's keep moseying on. So we have n equals 2. We're looking at the second derivative of sine, or the derivative of the first derivative. So a derivative of cosine gives us a minus sine of x. If we evaluate that minus sine of x at 0, well, that's going to give us 0. So the C2 coefficient is actually 0. All right, let's keep moseying on along. The third derivative of sine. Well, taking a derivative of minus sine gives us a minus cosine of x. Then evaluating that minus cosine of x at 0 gives us a minus 1. So the third coefficient here, or the second non-zero coefficient, will be a -1 in that numerator. But this is a third, so this is divided by 3 factorial. And remember, The third coefficient will be multiplying x to the power of 3 and so on. So I'm just going to highlight the non-zero coefficients we have so far. So if we're just looking at some of these terms so far, we have that one coefficient, which corresponds to the C1 term, and we have that negative 1 over 3 factorial that corresponds to that second term that we see up above. All right, let's keep going. If we look at the fourth derivative of sine, well, the fourth derivative is just equal to, well, the third derivative's derivative. So a derivative of negative cosine gives us a positive sine of x, and then sine evaluated at 0 gives us a 0 again. So the fourth coefficient is 0. And we can keep going on and on. And you might notice a pattern here. If we look at the fifth derivative now of sine of x, well, that's going to be a cosine of x. Evaluating that cosine of 0 gives us a 1. So the C fifth term, or the fifth coefficient, will be that 1 in that numerator divided by 5 factorial. And there's our next non-zero term, which corresponds to that coefficient 1 over 5 factorial that we saw up above. So you can probably see what's going to happen with all of the even powers. All of those coefficients just turn into zeros. The only terms that really survive here are the odd powers, just like we said when we were indexing the series before. And well, in this case, what we found so far is the first 3 non-zero terms of sine. What they look like is if we take that C1 term, that's just, well, 1 over 1 factorial, which is 1, and we multiply it by x to the first, because it's a n equals 1 case, that's just an x. Then if we take the next term that's non-zero, which is the C3 term, this is a negative 1 over 3 factorial, and we have x to the power of 3, well, because that's the n equals 3 term from the way our series is indexed here. And then we go to the next term that's non-zero, which is that fifth term, which is a plus 1 over 5 factorial, which means since n equals 5 there, we raise x to the power of 5. And you can probably see the pattern that's going to arise here. The next term looks like it's going to be the odd power, x to the 7th power, all over 7 factorial. The next term after that, x to the power of 9, the next odd term, all divided by 9 factorial, and so on and so forth. And that is our series for sine. Now, the subtle thing that you may have missed a little bit was we indexed our series above from n equals 0. And well, why are we getting all of these funky 2n plus 1 sort of in the numerator and denominator? Well, where those are coming from is we're really saying, you know what? I'm going to just skip all of those even terms entirely, since the only terms we see that are non-zero in this sign only correspond to odd powers. So rather than just having x to the power of n in our series with a lot of zeros in it, we can just say, you know what, only grab the odd powers. So that is where we're getting this sine is equal to the series from n equals 0 to infinity of negative 1 to the power of n. Again, because we see that oscillation in sign, or that alternation in sign between plus minus, x is raised to only odd powers, so 2n plus 1s, and factorials only of odd powers as well, so 2n plus 1 factorials. And that's where we're getting the Maclaurin series, or Taylor series centered at 0 for sine of x. Cosine of x is going to work out very, very similar, except if you remember, cosine of x only preserve the even powers. So rather than have the odd powers in it, cosine managed to snag only even powers. So we have x's raised to powers of 2n, and we have 2n factorial in the denominator. So if we write out the first couple terms, this will be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on and so forth. And that's really where the Taylor series centered at 0 or Maclaurin series for sine and cosine come from. Again, we didn't show the actual derivation of the cosine series, but it's very, very similar to what we did for sine. It's just that rather than the odd powers surviving or the odd terms surviving, it's only the even terms.